Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already subscribed to this channel, this is the right time. Okay, in the last video, I talked about pix2pix, image-to-image translation. We went through the original paper and understood every detail about the generator, discriminator, GAN, and how the training happens and all that stuff. So let's take that knowledge and apply to this image translation of satellite images into maps. So just a quick review. In case you haven't watched the previous video, I definitely want you to go back because then it makes more sense when we go through the code later on. But just a quick summary at a high level, you have a generator. And in this case, in pix2pix, the generator is a unit where it takes in a real image and generates a version of a fake image. And in this case, that version, we want that to be something that looks like a maps image. So this fake image along with the real image are going to be provided as inputs to the discriminator. And as you know, discriminator takes two inputs. One is real, one is fake, because the whole point of discriminator is to discriminate between a real image and a fake image. That means we need to supply a real image and a real image pair. So unlike regular GAN, here we are providing pairs of images, pairs of real and its equivalent version of the maps image. When I say real, I always refer to, in this case, satellite images. When I say a target image, then I'm referring to a maps image. Okay, and both these images will be concatenated like real A and real B. So if our image is 256 by 256 by 3, 256 by 256 by 3, when you add them together, you get 256 by 256 by 6. That goes into the discriminator. And again, half of these, they go into the discriminator. And the discriminator's job is to be trained on in understanding whether this image is real or fake. And during the training process, when you supply the real image, when you supply the fake image, you are labeling real image as 1, fake image as 0, and you're training the discriminator. And we are training the GAN, then you're actually fixing this discriminator, not training it, but then supplying a label of 1 to the fake image. So you're trying to fool the system. Okay, so the discriminator is being trained, and now you get discriminator loss, of course, and also the generator loss. And the discriminator loss, again, you update the discriminator, and then this is how you train it. Generator loss, of course, you go back to the generator, you update it. But in addition to the regular binary cross entropy based GAN loss, we also have another loss that goes into the generator that's called L1 loss. L1 is, as you probably know, is mean absolute error. What is the mean absolute error between? It's the mean absolute error between the fake image that the generator generated and the actual corresponding image to that real image, which is our maps image, the target image. So the difference between these two is your mean absolute error, or L1 loss, and this also gets added as a loss to your generator. And in fact, it's not just one-to-one adding. L1 has 100 times more weight than the GAN loss here. And I talked about this in the last video where the paper exclusively mentioned that they have tested various scenarios and they are proposing this. Okay, I think this gives us a good understanding. Now let's jump into the code and get started. And let us start by looking at the model. We did this in the last video, but again, for those of you who did not watch my last video, a quick summary of our pix2pix model. So first, let's import all the required libraries. Nothing to explain there. And in the discriminator, again, we have two inputs, as we just saw. One input is your source image, which is our satellite image. The other one is your target image, which is your maps image. So these are the two inputs, and they get concatenated, right? So when you concatenate them, you have 256 by 256 by 6 as your size right there. And then it follows through the architecture that these guys actually defined as part of the paper. So it follows C64, 128, 256, and 512. C stands for convolutional layers. And if you see CD, then that is convolution and dropout, I believe. So that is for the generator, by the way. In discriminator, there is no dropout. So let's go down and go ahead and look at this. So you have 64, 128, 256. And as the paper suggested, we are not including batch normalization as part of the first layer, but then it's part of the next few layers. This layer is, I added this. If you want, you can comment this block. This is just an extra layer. Yeah, you can just go ahead and comment that part out, and there you go. I think that's pretty much it. And we are using our Adam solver with a loss or a learning rate of 0.302. And beta is also suggested to be 0.5 as part of the original paper. So let's go ahead and run these lines, and let me comment these two out because I wanted to use it in my last video. And now let's define our generator, which is a unit that has encoder and decoder block and skip connections. So let us go ahead and define this. Define your encoder block right there. And define your decoder block. And there you go, the dropout right there. So which we do not have in in our discriminator. Too many models right there. Okay, so what do we do right now? And of course, you see there are skip connections right there. This is what it makes a unit and not just a regular encoder decoder, right? So you have your concatenation between your output here and the skip connections. Remember that. Again, I assume you guys know what unit is. If not, just subscribe my channel. Watch all the videos on unit. Okay, now we are defining our generator, which is a unit, and you have your encoder path, your base, and then decoder path. And finally, you have your final output layer. The only difference between what we have done in the past videos when we did unit and here is they're using an activation of tan H, which means your output image is going to have values between -1 and 1. So when you're pre-processing your images, make sure you normalize them or scale them between -1 and 1. Okay, so that's one additional point, but otherwise we can go ahead and run. In fact, let's not run any of these lines because we are going to import this from a different piece of code anyway. So let's go ahead and do that. Just understand the code. Now, we just looked at encoder and decoder and put together a unit. And we looked at generator. Generator is our unit is our generator. And we looked at discriminator. And again, discriminator is a patch GAN. Again, watch our video number 250, last one, to understand what a patch GAN is. So far we did that. Now we have to put them together as a GAN. That's what we are doing down here. We are putting them together as a GAN. And we fix our discriminator to be non-trainable. We do not want to train discriminator. We only want to train generator as part of our GAN. Typical GAN process, right? And also, in addition to this, while we are training our GAN, we want to make sure we have two losses. One, binary cross entropy, and the other, mean absolute error. And this is basically our L1 error. Our L1 loss. So you have these two, and we want our MAE to be weighted to 100. So there you go, and binary cross entropy is 1. So this is our GAN. And finally, we have a couple of other functions. When we call generate real samples, it's going to look at our data set and it's going to provide us with our train A and train B. Train A is the satellite image, train B is the corresponding maps image. So this is what it's going to provide us when we call generate real samples. And next one, when you ask for fake samples, of course, where do you get fake samples from? From the generator. It's generating the fake samples. So our samples are going through generator.predict, and then it gives us the fake samples. The label for fake samples is zeros. That's why our Y values are zeros. And here the Y values are ones because these are real samples. This is, again, our regular GAN process right there. And finally, we are ready to train. There is an additional function called summarize the performance. This is there so we can periodically come back and plot how the images are looking while you're training. Again, A GAN is not like your regular, let's say, training where it converges and you're like, oh, okay, if the loss doesn't increase by so much, go ahead and stop. GAN, you're training your generator against discriminator. So you want to find a good balance between generator and discriminator. So it's a bit challenging, or it's tough to find out when this entire thing is converging. That's why you typically train for a long time, a real long time, and then save these models periodically and generate plots periodically, or like fake images periodically, to make sure that things are heading in the right direction. So for that, there is a summarized performance right there. And all it's doing is it's generating these fake samples and then plotting all of these real fake samples as we are training. And so we can go ahead and look at them. And while we are doing that, it also saves the generator model right there. Okay, so that's basically the helper function that's going to basically summarize the performance. I don't know, every 20 epochs, 30 epochs, whatever the frequency that you choose. So finally comes our training process. Again, we are going to enumerate our epochs and batches individually, and we are not just doing model.fit, right? So we define our, again, train A and train B right there, and then we define our batch and number of steps. Okay, and then for each step, for each epoch, you can think of these as epoch. I mean, basically batch per epoch, we are going to work with one batch right there, as suggested by the paper. In the paper, they said, okay, for image generation, one batch size equals to 1 usually does a great job. So basically your number of steps here is equal to number of epochs. Okay, quick note. So for each of these, now we are going to generate real samples, train the discriminator, fake samples, train the discriminator, and then the generator, right? So that's our typical GAN process. So X real A, X real B, Y real, you generate your real samples, and then you generate your fake samples, then you train your discriminator on the real samples. Real sample is what? Real A and real B. Real satellite image and real maps image. And then your fake images right there is your real satellite image, but a fake maps image. There is no fake satellite image. We are not trying to fool the discriminator, or we are not trying to generate the satellite image. We are trying to generate the maps images. So your fake image data is basically your real A and corresponding fake data for maps. That's what your fake is. That's what we're trying to train here. And then you have you're training the GAN on your real A and these values, right? And we are going to print out the results, looks like for every epoch right here. And then we're going to summarize it. We're going to summarize the performance, meaning we are going to invoke this function to go through and then plot these results. I'm going to share this code, so don't worry. Let's go ahead and look at actual images and training and how the results looks like. I have already trained this for 10 epochs, not that long, 10 epochs, just to see how good the results look like. These GANs can be very slow, so hopefully you can throw this for a couple of days and get much better results. But let's see how good the results are even with 10 epoch training. So let's run all of these lines right there. And let us load the, I totally forgot where to tell you where to get these images. I think I have, yeah, up here you can find other data sets. Like when you click on this, it should take you to this page where you have cityscapes. I did not look at this image at all. I did not download. There is edges to handbags. So I think in the original paper, you see the sketch of the handbag and how you convert that sketch into a real handbag. This can be a great data set, obviously, to train your GAN. You can take exactly this GAN and train it on any of those data sets. It doesn't matter. And edges to shoes, apparently you can generate shoes. You can generate whatever that facades are. And you can actually generate night to day, same picture at night, same picture at day. So you can generate your day images if you have night images and so on. Maps is what I downloaded. And these images look like, when you download that and when you extract it, you get train and val folders, validation folders. Under train folder, there are 1000 images, and each image is a pair of an actual satellite image and corresponding maps. So this is a 256 by 512 image. So 0 to 256 in this direction, it is a satellite image, and 256 to or 255, let's say, and 255 to 512 is your maps image right there. So we have a whole bunch of these. So let's see if we can train our model on these images. So let's get back to our code, and first thing first, let's define a function to load the images. Now, why am I doing this? Because if you remember, our input images are 256 by 512. So we go from 0 to 256, which is our satellite image, and from 256 to the end of it, which is 512, is our map image. So we're going to capture them as individual arrays. So let's go ahead and run this function. And now let's basically give it the path to our images. This is the path. And now let's load the images. Okay, so it should be a bit slow, but not that slow. We only have 1000 images, so it should be there any moment. So we are loading both the source images and the target images, right? Again, source images, they're all the same in one single image. So 0 to 256 and 256 to here. Now, once we load those images, now let's go ahead and plot. So we know that, okay, they are loaded in the right way. So number of samples 3, that's okay. Let's go ahead and plot them. And I need to expand the top portion so we can see. So there you go. So this is your input satellite image, and this is the input maps, or target maps if you want to call it. Yeah, so these images are going into our generator and discriminator, and we're training those. So now let's go down. We already defined our pix2pix model. So from there, let's go ahead and import our define discriminator, define generator, define GAN, and a few other functions. So let us import those. And down here, it's defining our discriminator. Again, define discriminator is, where is it? Define discriminator. I'm just calling this function, that's it, by providing a input image shape. So let's come back. My input image shape is right there. So what is my input image shape? Go ahead, input image shape is 256 by 256 by 3. So that's what I'm providing to my discriminator. That's exactly what I'll provide to my generator. And now I'll put together a GAN model. What is a GAN model? Now we have to define our GAN. So if you go back, come down. Now I'm defining this, define a GAN. What does it take? It takes your generator, discriminator, and your image shape. So that's exactly what we are doing here. Generator, discriminator, and our image shape. So this is our GAN. And now we have to define what our data is, because our input actually takes our data set right there, right? When we train, we have to provide the data set. So my data is basically my source images and target images. Yeah, that's my data set. My satellite images and the equivalent corresponding maps images. Okay, finally, we are almost there. Now we need to pre-process the data. Again, pre-process how? Normally we divide our pixel values by 255, so we get our pixel values or numpy arrays of 0 to 1. In this case, our final activation function is tanh, meaning it goes from -1 to 1. So the generator is generating images with values between -1 to 1, which means it only makes sense for us to scale all of our images to values between -1 to 1. That's it. That's exactly what we are doing there. So let's go ahead and pre-process our data. Then it's a matter of training. So we can go ahead and train this. And I don't want to overwrite my. That's okay. Let's go ahead and train this so you can see exactly how it looks like while it is training. It's probably very slow. That's why I only did 10 epochs. So let us have a quick look at it while it is training. So yeah, this goes on for, I think, like, we can calculate that 1096 right there, right? So 10 epochs means we should see 10,960. So we are only at 60. So it takes time. Okay, so let's go ahead and stop it. I have done this already, so we can go to the second part, which is load the saved model. I did this for 10 epochs, so let's go ahead and load the saved model. And let's define a function to plot images. All it's doing is, again, taking our generated image and then plotting our source image, and then the output image, and then the actual corresponding label, so we can actually see how good we are doing. So let's go ahead and do that. And finally, let's define our data set and obtain a random image from the data set. Yeah. And go ahead and predict. Well, let's give our source image and target image. These are our inputs, and we need to go ahead and predict and finally plot. These steps are pretty straightforward. I'm not explaining this because this is literally, you're just loading a single image from a collection of images, right? You're getting a random image, and then you're basically predicting on that using our generated stored model, and then now we are just plotting the results. That's it. So let's go ahead and plot it. So here is our generated. That's what is expected. In fact, expected is the ground truth label. I actually like the generated one because you see like how you have this area right there. That's not even in the original. That's not even in the original image. I don't know why. Maybe that's not a path. But anyway, let's go ahead and run these lines and see a few images, a few results. So there you go. That looks pretty good when compared to your expected. Not bad. I mean, this patch, we haven't gotten that, whatever that thing is, but this is a pretty good approximation, I should say. Even for 10 epochs, that's not bad. Yeah, I'm very impressed with this. Yeah, I was looking for some greenery. There you go. This is not bad. In fact, you can see some of these areas. This is continuous up to here. But if you look at the original image, this is kind of patchy up to there. Nice, very nice. I hope you appreciate the strength, the power of these pix2pix based GANs. They are generating realistic looking images. That freeway, we completely missed it on the top. I wish I could train this model for 100 to 200 epochs, because these results are very promising, as you can see already. Okay, so I think we should stop right here. You got an idea. Now you have the toolkit. Go ahead and download this code. Go ahead and test it out. And I'm not sure if Google Colab is. I mean, it's pretty. It's not slow, but it disconnects like after 90 minutes or something of inactivity, so you constantly need to monitor it, but it's worth it. I mean, if you don't have your own GPU, go ahead and use that, but have fun with this. In the next video, we're going to generate realistic, very similar process, realistic looking scientific images. So instead of these data sets, I'm going to work on a data set that I have, that you all probably looked at many times if you are a follower of this channel. And you can download that. I'll provide a link for that anyhow. So come back for the next video and let's generate some realistic looking fake scientific data and use that power responsibly. Okay, guys, thank you.